Oh hey, didn't see you there. Let's meet the team.
A cursory look at an API reference documentation page will typically reveal a mixed bag of information items, including definitions, code snippets, specifications, how-to guides, implementation notes, references to other documents, and so on. Discerning what is important and relevant information in API documentation can be a challenging task given the size and complexity of API documents. For example, the Java Development API contains over 3 million words. Manually analyzing all of the knowledge and evaluating its worth and value is virtually impossible. So, we wanted to replicate the work of Dr. Fucci and others to identify types of knowledge in API documents. Furthermore, in classifying API documents, we can find areas of knowledge that we want to focus on and gather insight into how programmers interact with API documents in general. As there aren't global standards for how to document API, such as .NET, Java, and Python, we thought it would be interesting to replicate the "on using machine learning to identify knowledge in API reference documentation" study to understand what types of knowledge are most prevalent in different API documents. We referenced research done by Professors Rubelard and Malige, who identified 12 main knowledge types in API documentation and correspondingly labeled over 5,000 sections of Java and .NET API documentation. The training and test dataset is comprised of over 5,000 sections of text with manually evaluated multi-label classifications for the knowledge types of functionality and behavior, concepts, directiveness, purpose and rationale, quality attributes and internal aspects, control flow, structure, patterns, code examples, environment, references, and non-information. A portion of this dataset was publicly available with the links to the Java and .NET text. We attempted to scrape the text using the links provided. However, the links were now outdated versions, and the sections of text we hoped to scrape were inconsistent for scraping to be viable in the time frame of our project. Fortunately, after some email correspondence, Professor Rubelard and Dr. Malige were able to provide us with a copy of the full Cato dataset. Before we began training our model, we transformed the text input into something that our machine learning models could interpret. We began by removing all the stop words and noise contained within the text, and used a bag of words algorithm to convert the text into integer values based on term frequency and the inverse of their term frequency. Once completed, we classified the 12 knowledge types with a one-verse-rest classifier, which splits up the label classifications into one binary classification problem per label. Afterwards, we used k-fold cross-validation to get a general understanding of the efficiency of a given algorithm, and to reduce over and underfitting for our datasets. The 6 machine learning algorithms we decided to test the dataset on were k-nearest neighbors, support vector machine, random forest, logistic regression, multinomial naive Bayes, and gradient boosting. Coming into this project with minimal experience in machine learning and natural language processing was intimidating to say the least. However, we learned a lot about the capabilities and limitations of both machine learning and deep learning algorithms as they pertain to natural language processing. Our familiarity with research papers, especially those in the software engineering field, has improved dramatically. We all feel comfortable navigating such papers, scanning for valuable information, determining the context of references, and formulating an understanding of the goals and outcomes of the researchers. Substantial progress has been made on our project. However, improvements and optimizations can always be implemented. Although relatively satisfied with our results, we would like to further fine-tune our machine learning hyperparameters. Implementation of deep learning algorithms would also be beneficial for more direct comparisons to the results obtained in the aforementioned study. Additionally, looking into recent research with transformers and natural language processing, implementing a transformer to work with these datasets, and observing if the transformers perform significantly better than the deep learning models used by the researchers is also something our team would like to look into in the future.
Nice. Perfect.